This is linear algebra. We're gonna study vector space. So from now on, all concept is very abstract. You guys understand the definition, which I give, and then have some good example to understand the definition of chapter 4, guys. Okay? So I'm gonna give specific example how gonna prove such concept, but you have really pay attention, guys. Okay, first, what is vector space? So when you're talking about definition of something in this chapter, you have understand definition. That's gonna be we gonna accept as it is. You don't can argue about that. So vector space gonna be, guys, non-empty set of vector. You correct all the vector we studied so far. Then we're gonna define the two operation. First is addition. We're gonna talking about addition, add to vector. Second is scalar multiplication. We're gonna define it. Depends on the vector space, guys, such that you satisfying follow axiom. Okay, you have 10 axioms. You have proved 10 to show space is vector space. Okay, first is, guys, look at this. First one is addition is going to be add to vector, go to the vector space, V, vector space some set. Commutative, add, order doesn't matter. Vector u plus vector v plus vector u. You have to keep the, you're gonna thinking about commutative. Third one is association rules, guys. Vector A, vector V, U, vector V, and then vector W later, or add the vector V, vector W, add vector U later. We say that's the association rule. This one is very important. Zero vector should be vector space, and you're gonna zero vector plus any vector add together. That's gonna be U vector. Okay. Fifth one is any vector you pick to the vector space, vector u plus negative vector always add together. That's going to be zero vector. That's all related addition operation, guys. Okay. Right side is about the scalar multiplication. So C, D is real number. That's we call this one is a scalar, right? So C times vector gonna be vector space. C gonna be scalar multiplication. You can distribute. Okay? C plus D, that's two scalar. You can distribute two. C U vector, C V vector. Scalar association. You're gonna do this one first, scalar multiplication, and you time the scalar later, or multiplication of two scalar and then times vector U is the same. Last one is one, number one times U vector, always U vector, guys. That's the 10 actions you have to prove for the vector space, guys. Just to follow the each action for the example or practice problem. Okay, first one is V gonna be, guys. I'm gonna give the V vector V set. This one is a subset of R2. What is R2? Two entries. What is R2 represent, guys? R2 gonna be represent rectangular coordinate. Everyone understand that, right? X is this is X, this is Y. Which region they represent the V, guys? X is greater than equal to 0, Y is greater than equal to 0. So that's talking about our first quadrant. So this one is quadrant 1, okay? So this is vector space. You have proved all the 10 axioms, but you cannot prove it. We call counterexample. You're gonna give some example, it doesn't work, okay? So let's just start this one first, guys. Before we do it, guys, first you have defined addition. So let's put the two vector first. Vector 1 is x1, y1. Vector v is x2, y2. Okay, so we're gonna addition is u vector plus v vector gonna be you add each element, right? Okay, how about scalar multiplication? C gonna be real number. You're gonna define cu vector gonna be cx1, cy1. That's you defined addition, guys. This is addition. Here is a scalar multiplication. It's daunting job to prove all the 10 action, but look at this one is simply you can give the counterexample why V is not vector space. I can say, guys, let's give the one example. Can you thinking about one example? This cannot be vector space. Okay, I'm gonna give this one, guys. So U vector is gonna be 2 and 1. Where is 2 and 1, guys? Can you sketch it? 2 and 1 is gonna be 2, 1. That's the U vector. Of course, this is the first quadrant. Now, I'm gonna pick C value gonna be -1. Any real number you can pick. So you're gonna find the CU, scalar multiplication. So -2, -1. In the picture, where is -2, -1? That's the here. So negative CU vector. Another way, no. CU vector, that's the negative U vector. This vector is quadrant 1, which meaning is you can say -2 is greater or equal to 0, -1 greater or equal to 0. Yes or no? This is totally false, right? So you're going to say CU factor is not V, which meaning is, guys, you're going to conclude, you're going to say V is not a vector space. Everything makes sense? We call this in counterexample. So you prove, you pick the one vector from the V and you times C, scalar multiplication, then you prove this cannot be in the V set. Okay, that's we call counterexample. This is not a vector space, okay? Get some idea, guys? Okay. So let's do another example for the vector space, guys. So here is xy, multiplication xy is less y equal to 0. What does this mean, guys? First you understand this means, okay? This one. Xy is gonna be R2. So you're gonna see rectangular coordinate. What does this mean? Xy is less y equal to 0, right? So meaning is the sign of xy should be different. The first condition is x is less or equal to 0, which meaning is y is greater than equal to 0. Or x is greater or equal to 0 and y is less or equal to 0, guys. Make sense, guys? Then what is this one? X is less than 0, y is greater than 0. Which quadrant they talking about? This one is quadrant 2. So what is this second one? X is greater than 0, y is less than 0 is quadrant 4. So I'm gonna sketch, you're gonna consider only quadrant 2, quadrant 4. So can you think about it? This one, guys, this one is vector space, or you can give some counter example. So R2 is have addition and scalar multiplication we talk about so far. So let's thinking about any example, guys. Let's say U vector gonna be -2 and 2. So that's the second quadrant, -2 and 2. So I'm gonna put this U vector. Right, guys? V vector gonna be, you're gonna pick V vector is 3 and -1. 3 and -1, 1, 2, 3, -1. You're gonna put the V vector right there. Then let's find addition of two vector, guys. Let's find it, guys. Addition of two vector, U vector plus V vector. What is gonna be? -2 plus 3, 2 minus 1. So this one is 1 and 1. Where is 1 and 1, guys? Where is 1 and 1? That's in quadrant 1, right? So 1 and 1 gonna be here. That's the 1 and 1. Guys, make sense? So here is addition of two vectors, quadrant 1. So this one is meaning is u vector plus v vector is not v set, which meaning is v cannot be a vector space. So we give the counter example why V is not a vector space, okay? All right. So you guys practice this example, guys. This one is vector space or not? Get some idea. How can you gonna prove it? This one, guys. All right. How can prove it? So I gonna say, can you have any idea, guys? Pause the video. You're gonna try to think about a little bit. Okay, did you go through all the 10 axioms for the vector space, but you quickly find something, guys. I can find counterexample gonna be, guys, zero vector. Zero vector gonna be 0 and 0. In the V, can you think about it? Zero vector is there. Why not? So you cannot say 0 in the V set. Here is a V vector, this set gonna be X element, Y element, always 1. So here is X gonna be 0, Y gonna be 0. So X times Y equals 0. It cannot be 1. So we're gonna say 0 vector is not in V vector. That's a violate action 4, guys, okay? So we cannot say, guys, conclusion is V is not a vector space. So violate one action, we cannot say vector space, guys. So you keep practice, get this kind of example, you're gonna master it, guys. Next one is I want to talk about, guys. I want to talk about what is vector space in the linear algebra. So this is very important vector space I'm gonna give to you right there, guys. So here you go. Rn. We already talked about Rn. Rn is you're gonna correct the vectors. So for example, you say R2. What is R2? That's gonna be vector space only two element entries. So A1, A2 is real number. So that's the R2. That's the vector space. R3 is, guys, remember that? This one is a 3 element. That's the vector space, okay? Matrix, set of matrix, M by M matrix. That's gonna be vector space, guys. This is vector space. So for example, M2, square matrix, entries only 4, 2 by 2 matrix. This is A11, A12, A21, A22. That's gonna be vector space. We can say M3, 3 by 3 matrix, vector space, so on, guys, okay? Last one is, this one is a polynomial with degree n. So this one is vector space too. Okay, correct all the polynomial with degree n, we call vector space. We're gonna practice very specific vector space. Okay, we want to show P2 polynomial, quadratic polynomial is vector space. You and I gonna show this is a vector space. So we have proved all the 10 axioms, okay, guys? So one by one, we're gonna check it, why this is vector space, all right? So P2, guys, we wanna show it, it's really long step. So first polynomial is with degree 2, A0, A1t plus A2t squared. So Qt gonna be another polynomial with degree 2, B1, B0, B1t plus b2t squared. You pick the two polynomial with degree 2 first. Let's define the addition. P plus Q. Sum of polynomial, the pt plus qt. Guys, can you do that? Add this one together. So a0 plus b0, same term. a1 plus b1t, a2 plus b2t squared. So this one is polynomial set with degree 2, of course, right? Then you're going to show the commutative association rules. You can look up my notes. Another is you can check the number 2, p plus qt. Another way you say pt plus qt. Of course, this one is qt plus pt. Very easily prove it. Number 3, association rule. Another polynomial r, you can do q plus r. Okay? Number 4 is we have find the zero polynomial. How can we find the zero polynomial is, guys, 0 plus 0t plus 0t squared. So that's the zero polynomial. Of course, this one is p2. Also, 0 plus pt, that's going to be pt. Guys, make sense? Okay, number 5, negative polynomial, meaning is pt, you give right there. Negative pt gonna be negative a0, negative a1t, negative a2t squared, pt plus negative pt, always zero polynomial. That's obvious, right? Now, this is all additional polynomials. Now, 6 is scalar multiplication. So C, pt gonna be what, guys? C, a0, a1t, a2t squared. That's gonna be C, a0, c a1t, c a2t squared. Of course, this one is p2. Okay? So same thing is you can prove C plus D, pt, gonna be cpt, dpt. Very easily you prove it. A gonna be C dpt and C dpt. 9 gonna be what, guys? 9 gonna be what? We missed something. C pt. Oh, C pt plus qt. That's gonna be C pt plus C qt. Okay, I'm gonna skip here, guys. So 10 is 1 times pt. 1 is what? 1 times a0, a1t, a2t squared. You times 1 each term, same thing. So this one is pt. So we prove all the 10 axioms. You're going to say what? This one is vector space, okay? That's how I prove it. It's a tedious step, but we have proved each axioms, guys. Last one is you guys practice it, but I'm going to show how can define the addition and scalar multiplication. You can prove all the 10 axioms, guys, okay? So here I'm gonna define addition of two vector. So here is R2. So I'm gonna define the U vector is X1, Y1. V vector is X2, Y2. How can define the addition of two vector? This one is X1 plus X2, Y1 plus Y2. Of course, this one is R2, right? Another one is a scalar multiplication. Let's say C gonna be real number. CU vector, how can define it? CX1, CY1. Of course, this one is R2. Its entry is R, right? So let's see zero vector. How can define the zero vector? That's gonna be 0 and 0. This one is R2. Okay? Negative vector in R2. Okay, so UV negative, you can see negative X1, negative Y1. This one is R2. So you can try to show all the commutative association of addition and scalar multiplication. It's not the hard proof to show this R2 is vector space.